here's an energy equation for a fluid system. In general, this is a general energy equation. Again, energy equations just means E in equals E out. And in general, a fluid system, of course, has its elements from the Bernoulli equation, where we have the potential energy term, we have the kinetic energy term we recognize because we have a v squared in there, we have a height for potential energy. That came from, kinetic energy 1/2 mv squared term. Potential energy is a rho gh, and we have crossed out all of our densities in here. But and this is our pressure term in the middle of Bernoulli's equation. So in a fluid power system that also has a pump and a motor and real losses, we would start with a certain amount of energy at position 1. We have a certain amount of energy at position 1, and then we have a certain amount of energy at position 2. So the energy in and the energy out, energy is not created or destroyed. It only changes form. Those are going to equal each other, but we see there's a lot more potential energy here than there is down here. So it must have changed into something else. Increase in the kinetic energy, for example. But what if we are pumping something up, or we're pumping something down? So we are adding the motion of a pump, and then we are subtracting the electrical energy that went into supplying the motor that is going to run that pump. We lost some friction because of that pump. So let's say we're going to go the opposite way, and we're going to pump upstream here. We're going to pump from position 2 to position 1, or let's just rename this position 1 and position 2. Then I'm going to have the position 1 is now going to be smaller than position 2. So H1 is smaller than H2. I'm going to have the pressure out 1, and then I'm going to have the velocity at 1, and it's going to be different than the velocity at 2. That's going to be actually slowing down, and this one's increased because it's a smaller diameter. But here, I put a pump at the bottom of the system, and the pump is going to make the fluid flow up. So I had to add a lot of energy from that pump. But the energy that pump is going to put in, some of that was used to run the motor, and some of that is lost due to friction. So I must add so much to pump this to account for what the motor needed and all of the losses of pumping this up due to friction. So this is an application of the energy equation, in which we would use Bernoulli, but then we added a pump and a motor to the system, and we added some losses to the system. We can look at this the other way around, and we can say, oh, here's a hydro system where there's lots of potential energy up here because of this height. And then the potential energy turns into kinetic energy, and then that turns into electrical energy as well. So we can add to the Bernoulli equation some extra terms in to account for spinning a turbine here and making electrical energy out. So in general, this energy equation for a fluid system is only one equation. And that equation is whatever energy is in is going to be the same total amount of the energy out. Sum of the energy in is equal to the sum of the energy out. You're going to have a lot of terms in, you're going to have a lot of terms out, and it's just a matter of balancing those, making sure that you can cross out your densities and everything, and then you have the variables you need to solve these design problems.